Okay, I think we can start. We are already 2 minutes over. So, good morning. Hello, everyone. Welcome to another talk in our webinar series. Today we have Dalya Baron from the Tel Aviv University, and she will talk to us today about machine learning in astronomy. Before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link in our website, or you can access it in our YouTube channel, LIneA MCTI. Dalya, thank you very much for being with us today, and the floor is yours.
Thank you very much, Rodrigo. I'll share my screen. Can you hear me okay?
Okay, we can hear you, but you're okay. Now we can see your screen.
Okay, great.
Perfect.
Okay, great. Thank you, Rodrigo. So thank you very much, first of all, for inviting me here, and secondly, for coming up this early to hear my talk. Today, I'm going to give you a very brief introduction to machine learning in astronomy. This is an exploding field. It is a huge field that grows exponentially every day, basically. So I will touch upon several things inside this very big field, but I will then give you a few references of where you can learn more about the things I'm going to show you. So I want to start with a revolution that astronomy has gone through in the past 2 decades or so. I'll start by showing you a paper from 1985. This is a paper by Donald Osterbrock and Richard Pogue, where they present spectroscopy of 6 galaxies. You can see here an example of one of the spectra they got. And from these spectra, they can learn various properties of these galaxies. They can know the redshift of the galaxy. They can study the stellar population, so the age of the stars, the velocity field. They can also constrain gas properties, again, the velocities, the dust and metal content, densities, temperature, etc., etc. And what I'm showing you here is, in some sense, a traditional paper from 1985, a very good paper. It has nearly 800 citations the last time I checked. And it taught us a lot of new things in this field of narrow line Seyfert 1 galaxies. So this was the situation roughly until 2 decades ago. And then things have changed dramatically. So the volume and the rate of the information that we have in astronomy today, it grows exponentially. And the sky surveys that we have operating now generate petabytes of data and derived products. One of my favorite examples is the Sloan Digital Sky Survey. This is a large survey that provided us with multi-band images of roughly a third of the sky. And it gave us spectra of millions of galaxies and stars. You can see here a diagram showing the galaxies within the SDSS footprint. We're sitting here in the middle, and every point here in this diagram is a galaxy, and it has a spectrum, which we now have as well. So imagine all the things we could learn from a single galaxy spectrum. Now we have millions of them lying in our databases. This is in terms of optical spectroscopy and imaging, but if we go to time domain, we now have surveys that basically monitor the night sky, such as Pan-STARRS and ZTF, and provide us with time series, so information as a function of time of various variable sources. We also have Gaia that have given us positions and velocities of roughly 1 billion stars in the Milky Way. So the amount of data we have today is insanely huge compared to what it used to be 20 and 30 years ago. The second type of thing that happened is not connected to the data size, but to the data complexity. So we have today different telescopes and instruments that map astronomical objects throughout the entire electromagnetic spectrum. You can see here an example of a galaxy that was observed in visible, infrared, submillimeter, radio, and X-ray, and you can see different features in these different images. And we have various astronomical objects for which we have this multi-wavelength information. So the complexity of the data is much larger. In addition to that, in time domain surveys, we have multi-band time series, so not a single band, but multi-bands. And we also have not really new players, but integral field units, again, became operational in the past 2 decades. These provide us with spatially resolved spectroscopic information. So these are either optical or infrared IFUs, or when we're talking about radio interferometry, in such a case, we no longer have an image of a galaxy or a single spectrum, but rather we have a spectrum from every point in the galaxy, from every resolution element. And again, all the things we could learn from a single spectrum of a galaxy, imagine now what we can learn from this huge data set that covers a single galaxy. In addition to these changes, we now collect information not only from our universe. So we have large-scale simulations today that simulate our universe, and they produce rich and complex data sets, and they give us mock observations of galaxies. Here I'm showing you two diagrams from this review in Nature regarding hydrodynamical simulations of galaxy formation. And we can see here the large-scale structure and galaxies. And basically in simulations like Illustris TNG 100, we have millions of galaxies as well. And in each of these galaxies, we can have tens or thousands of resolution elements. And these resolution elements, again, give us a lot of information about the gas, the stellar content, etc., etc. So this, again, constitute one of the significant parts of the data that we now have in our hands. So what is fundamentally different now compared to what it used to be in the 1980s? First of all, we can no longer inspect all of the data by eye. There is just too much of it. I cannot inspect 2 million galaxy spectra by eye. Since the data is extremely complex and multidimensional, I can no longer visualize correlations and patterns. If I have hundreds of measured features per galaxy, it is very difficult for me to explore different correlations in this dataset. And this increase in information content basically gave rise to a new type of scientific methodology. The traditional scientific methodology is the hypothesis-driven science. We start with a theory or a scientific question, and then we design some sort of an experiment or perform an observation, which we then analyze and extract knowledge from. This is how we learn new things. Since the information content in the data increased dramatically, we now have data-driven science as an additional scientific methodology where we actually start with the data set. We perform some sort of data exploration, and this data exploration informs us about a hypothesis. So we do not start with a scientific question, but rather we let the data tell us where we should look and what we should do. Once we form this hypothesis, we perform an analysis, and again, we extract knowledge. In addition to this, when we look at simulations, so these things true for simulations as well, for simulated galaxies. But in addition to that, when we're talking about large-scale simulations or high-resolution simulations, we can no longer rerun them again and again and change the various tuning parameters that we're interested in. So even exploring our models have become extremely difficult. Now, I'm listing here some of the challenges that we face in this big data era that we've entered. We need to understand how we clean, how we sort, and how we store the information. We need to understand how we perform classification and regression. How do we generate new data or predictions from model? And most importantly, how do we discover new phenomena in our dataset? And this basically all connects to data mining. Data mining is a field in its own, and it connects various fields and various disciplines. And what you can see here is that machine learning is only one discipline in this data mining discipline. And what I want to note is that machine learning is just one of many tools that we as astronomers should have. We should understand algorithmics and statistics and visualization and database technology and physics, of course. This is in other disciplines here. And we need to understand machine learning. It will help us in some cases to do our job better. And in this talk, I'm going to focus on this tiny box here as much as I can. And as I said, this field is huge. It's exploding, and there are so many algorithms and so many applications and many new publications every day. So I will not be able to cover even a tiny fraction of what is done in the field. But rather, I'm listing you here two overviews, which I think could be relevant to people who are interested in machine learning in astronomy. The first one is by me from 2019, where I try to give a practical overview of different machine learning algorithms, of different tools that we can apply to our dataset, where I try to note the specific challenges we face as astronomers and as scientists when applying these tools to astronomical datasets. So if you're interested in understanding how these tools work, how do we optimize them? How do we analyze our input data, and what do we do for processing and things like this, please see this paper here. If you're more interested in applications, so different applications and different things that we have learned using machine learning, I strongly suggest to read this very nice review. It's also very recent, I think from 2 years ago. And I was told that most of the audience are not expert in machine learning, so I will try to explain the basic things, the basic flavors, let's say, of machine learning, and give you a few examples. And at the end of my talk, I will show you a few examples of my own work. So the first thing I want to discuss are supervised machine learning algorithms. So in these algorithms, I have a list of objects with some measured properties and some target variable. And what I want to do, I want to train an algorithm to take these measured properties and to predict the target variable for objects for which I do not have this target variable. So let's take an example. Imagine that I have a list of galaxies for which I have measured various properties, the ellipticity, the asymmetry, the concentration, the Gini coefficient, etc. And I have a morphological classification of the galaxy, whether it's late type or early type galaxy. And what I want to do, I want to take these measured properties and this morphological classification, and I want to put them into a supervised learning algorithm. What this algorithm does, it basically, each time it trains on this input data, trying to improve its own model such that the predicted morphological class will match the class that I gave the algorithm. This is the training stage. The algorithm basically learns from the examples I gave it. Once the algorithm is trained, then it can be applied to galaxies for which I do not have a morphological class. So in this type of learning, we can either do classification or regression. And there are several popular algorithms. Support vector machine, decision trees, and random forest, and various types of artificial neural networks, both shallow and deep. And in the next several slides, I think that the best way to explain what these things do is to actually show you a few examples. I think these examples are important because using these examples, I can at least argue why machine learning can be important in our field. So in this particular example, this is a morphological classification of galaxies, where we have a set of distant galaxy images. And from these images, we extract various properties of these galaxies. And then we take a supervised machine learning algorithm called an SVM, support vector machine, and we train it to predict the morphological class. And I remind you again that I need to have a sample of objects for which I already know the morphological class. This is the only way in which I can train this algorithm. And once this algorithm is trained, I can take it and apply it to galaxies, to galaxy images and set of measured features for which I do not know the morphological classification. And then I basically get a morphological classification for a very large set of galaxies. So usually, at this first stage of constructing a data set, an expert from the field need to go over their data, need to go over their images and provide these labels, late type galaxy or early type galaxy. And using this data, they can then train an algorithm to automate this process. Here, every time I'm putting an arrow like this, it means that it trains using examples I provided, examples where we know the ground truth, where in this case, it's the morphological classification. This is another very interesting example. This is from the time domain. So here in this example, this is from PTF, from the Palomar Transient Factory, where they basically monitored a patch of the night sky every night, obtaining images of different sources. So every night they have an image of a source, and they also have a reference image of the same source taken in the past. And what they can do, they can subtract the two in order to produce a difference image. And if something changed in this source, for example, a supernova exploded and we see the light, we expect to find some residual here, which will tell us that there is some sort of a variable source there. But it's not the only way for us to get residuals here. So the different PSFs during the night, various artifacts in the instruments and when we obtain these images, moving asteroids and things like this, all of them can affect the new image and basically produce some residuals here. So in this paper by Bloom et al., they used these difference images and extracted various features from these images. These features include things like the magnitude of this candidate, its semi-major axis, semi-minor axis, perhaps some information about a nearby galaxy, if there is a galaxy there. And again, they had an initial data set for which they have classified by hand whether this is a real transient event or some sort of an artifact. And they trained a random forest on this smaller data set. And once the random forest is trained, it can be used to automatically classify new objects. So every night, they have a stream of new images from the sky coming in. They can apply this trained random forest, and this will basically output whether this is a real variable source or an artifact. And for the real variable sources, we can then apply follow-up immediately. So basically, instead of having humans in the loop, which will go over the images and will classify them by hand, these random forests can do it completely automatically. So in these two cases, I showed you examples where we have some data, and then we extract a set of measured features from it. And these features, both here and here, had to be carefully engineered. We need to understand the physics of galaxies, and we need to understand the physics of transients and the physics of the artifacts in our cameras in order to construct a list of features which can be informative for an algorithm such as this. So we need to have a lot of domain knowledge. Here, I'm showing you another interesting example, but now we're looking at a regression problem. So instead of predicting a class of an object, we're predicting some continuous variable. And one of the most interesting examples is, of course, photometric redshift, where we have photometry of different astronomical sources, and we want to infer from this photometry the redshift of the source. So in this paper by Hoyle, he took images of galaxies in different bands. And again, in a similar fashion, he extracted a set of photometric features, various magnitudes and colors that he can extract from these images in different bands. And using this set of photometric features, he then trained something that is close to a random forest. It's not exactly, it's a different type of forest. He trained it in order to predict the photometric redshift of galaxies, basically. Another approach he has shown in his paper was taking these images, applying some transformation to them in order to obtain a different set of images. These are particularly color images. So he measured the magnitudes in each pixel and then defined color images. And then he took these images and used a convolutional neural network, which is also a supervised learning algorithm that takes as an input these images and outputs a photometric redshift. In both of these cases, the training, the objects for which we know what the redshift is a spectroscopic redshift. Okay, so once these algorithms are trained, they can then get photometry or these images and extract a photometric redshift. And this is basically the first example I'm showing you with deep neural networks. These are called convolutional neural networks, and I'm going to show you a few additional examples. These type of networks revolutionized some of the fields in astronomy. It is extremely exciting to see all the new developments and new things that come up in this field of deep learning in astronomy. And I'm showing you just two examples, but really there are many, many of them. One of my favorite examples is detection of galaxy strong gravitational lenses. So strong gravitational lensing is a rather rare phenomenon. And when we look at a data set, we expect these type of images with these type of nice arcs to be extremely rare. It is very difficult to find them. And when we have data sets that contain tens or hundreds of millions of images, it is very difficult to go through them by eye and find candidates of these strong gravitational lenses candidates. So in this paper, they took a set of simulated galaxy images, a very realistic simulation actually, where there is gravitational lensing. In some of the cases, it is easier to see, and in other cases, it is difficult to see. And since they have simulated the data by themselves and put in the strong gravitational lens that we see here, they have the label. They know whether it contains strong lensing or not. And they trained this convolutional neural network. And once it is trained, it can be used to find strong gravitational lenses in actual real data sets. So taking images, for example, from the upcoming LSST, and basically classifying whether these images have strong gravitational lensing signal or not. And this is, I think, a very important example of things that we couldn't really do before deep learning. It was very challenging for us to do things like this beforehand. Another nice example is the example shown here, where the authors Xu et al. Tried to identify stellar feedback bubbles in CO emission. Here again, we're using convolutional neural networks, and they do here both classification and regression. And the reason I like this example is because here the input dataset is actually a cube, a spectral cube. So we have the spatial dimensions, X and Y, but we also have a wavelength. So we have spectral cubes around the CO emission. And what you can see here, the output is now two-dimensional. Up until now, I showed you examples where the output is either a class or some sort of a continuous property like the photometric redshift. In this example, they actually output an image. And what is happening here? Here, again, these are simulated cubes using a hydrodynamical simulation they performed, where they know where they have stellar feedback bubbles, basically gas that is outflowing due to stellar feedback and forms this sort of bubbles. And these bubbles are actually, one can identify them through the velocities and momentum of the gas that is outflowing, which is something that is easier to do in simulations than in actual observations, obviously. So they train this convolutional neural network where the ground truth is the location of the stellar feedback and the fraction of the mass that comes from the feedback. So basically every pixel here can have a contribution from stationary turbulent gas in the interstellar medium, and it can also have a contribution from outflow emission. So once this convolutional neural network is trained, it can then be applied to actual observations, actual cubes, and then its output will be the region identified where we find stellar feedback and the fraction of the mass coming from the feedback. So this is, again, I think, a very beautiful example where we can use simulations. If these simulations are good enough and they can represent the complex physics in our systems well enough, then we can use them to train these algorithms and then apply these algorithms to actual datasets, to observe datasets. So perhaps you want to ask me which type of algorithm should we use? I've shown you several algorithms. I've showed you SVM, artificial neural networks. These are smaller networks, random forests, and deep learning. These are all these CNNs that I showed you. And these are very different algorithms. And again, unfortunately, I do not have time to explain how these algorithms work, but I want to give you a few pointers, a few things that are different in these algorithms. First of all, in terms of the input dataset, SVM can work only if we have a relatively small number of features. It will crash if we'll try to train it on a data set with thousands of features. Artificial neural networks and random forests can accommodate larger number of features, hundreds even. And in deep learning, we can have thousands easily. We can apply it to the raw data, to actual images, to actual spectra, to actual light curves of stars. So the number of features here can be very large. In terms of the size of the training data, for support vector machine, it can be small. I do not need a lot of data in order to train the algorithm to basically to predict something I'm interested in. For artificial neural networks and random forests, I need to have tens of objects at least. It's always better to have more examples, but if I have tens of objects, I can do a pretty decent job. And in deep learning, in most of the cases, I will need more than 1,000 of objects. In some cases, I will even need tens of thousands or 100 of thousands. It really depends on the type of deep learning that I'm building. Another type of aspect is the model complexity. So SVM is rather simple. The model does not contain a lot of parameters, whereas in artificial neural networks and in random forest, it is mediocre. There are a few parameters that are optimized during this training stage. In deep learning, we're talking about extremely complicated networks that can have even millions of parameters that are optimized during the training process. In terms of the free parameter that we can change and we can explore, basically, in support vector machine and random forest, we have roughly 4, which we can play with. In artificial neural networks, I'm writing roughly 10, and in deep learning, much more than 10. Basically, for neural networks, one of the challenges is how we build these networks in the first place. There are so many ways to build these networks. So the number of different choices can be huge. In terms of overfitting, support vector machine, because it is a simple model, in most of the cases, we will not overfit our data. In artificial neural networks and random forest, we sometimes can. overfit the data. And in deep learning, this is more likely. And this is something we need to think about if we apply deep learning to our data set. In terms of interpretation, since we're scientists and we're interested in understanding what is going on and why the algorithm decided to predict one class versus the other, in SVM, since it is a rather simple model that cuts the parameter space using simple lines or functions, it is easier to understand what is going on and why the algorithm performed the classification it had. In artificial neural networks and in random forest, it is more difficult. And in deep learning, it can really be a challenge. And a lot of work by astronomers and computer scientists today is devoted into making these networks more interpretable, developing tools that allow us to understand why these networks predict the thing they predicted. So I've shown you different properties of these different algorithms. And here we're starting with less complex algorithms and go to more complex models. And we can see here that for deep learning, we have more complex models, more free parameters, more challenging to interpret. Why should we use them? So this model allows us to analyze extremely complex data sets. When we use traditional statistical tools or more traditional, simpler machine learning algorithms, we can solve problems which do not have a lot of features and are not extremely complicated. But if we want to be able to classify images of animals or classify images of galaxies or jets or whatever, we really need to allow for a more complicated model. And in this case, deep learning really has been doing a revolution in astronomy. So a note about the input data. In some of the cases, I showed you that we're using a set of measured features. We take our initial image or our initial spectrum or time series, and we extract various features. In different algorithms, I showed you that we can use the actual images, the actual raw data. So what are the differences or the things we need to think about? Each of them obviously has advantages and disadvantages, and it really depends on the type of thing that we want to do. But I wanted to give you some general description of the type of things we should be thinking about. First of all, when we extract a set of measured features, we can use less complex models like SVM and random forest, which are easily run, they are more interpretable, etc. When we use the raw data, images or spectra, we have to use more complex models like deep learning. In terms of our scientific knowledge, so when we use a set of measured features, I list here allows and requires because it is both an advantage and a disadvantage to incorporate our scientific knowledge. So it's an advantage because if I study galaxies and I understand galaxies, I can build a list of properties, of measured features that are indicative of the morphological class of a galaxy. So I can use my scientific knowledge in order to make this task easier for me. On the other hand, the disadvantage is that I'm required to understand galaxies. If I have a data set in which I'm not sure that I understand completely what types of objects I have in my data, it is very difficult to construct a list of features which will be good enough to apply with a machine learning algorithm. When we work with the raw data, it allows us to construct more general models that do not depend on how we consider galaxies and what we think galaxies look like. On the other hand, in many cases, we still need to somehow incorporate our scientific knowledge in the deep networks in a different way. Let me show you an example. So when we're talking about galaxy classification from images, we as astronomers know that the classification of an image should not depend on the rotation of the galaxy or on whether I flipped the image or not. A late type galaxy will be late type galaxy, regardless of the angle from which I observed it, from the line of sight. And these things are not trivially incorporated into the deep nets, and we should somehow add this information in a different way. So people are doing it using a process named augmentation. They basically take images of galaxies and rotate them and flip them and use all of these as the input data set to make these networks rotational and flip invariant. So we need to do it in a different way. The final thing is regarding the amount of information. So when I use a set of measured features, I will have some information loss, okay? I lose some information. I cannot escape it. And perhaps most of the relevant information is captured in these features, if I understand the physics correctly. But I lose some information and some of it might be relevant. When I work with the raw data, I might have a different challenge of having too much information. In deep networks, this is less of a problem. When we're using more simple models, this is a problem indeed, and we need to think about whether we want to remove some of the information. So all of that was a quick summary of supervised learning in astronomy. Now I want to move to a different type of machine learning algorithms, and these are named unsupervised machine learning algorithms. And this in this family of algorithms, I no longer have some sort of a target variable, some sort of a ground truth, a galaxy class, a redshift, and things like this. But rather, I have some sort of an input dataset, a list of objects with measured features, and this is the input to the unsupervised learning algorithm. It has a cost function that depends only on the data that I inputted, and the output is some sort of a target variable. And using that, we can find patterns in the data. The common tasks that we're doing using unsupervised machine learning are clustering, dimensionality reduction, and outlier detection. In clustering, for example, we have some input data set. Imagine you have a list of planets where you measure the planet radius, the planet mass, the period around the star, the host star properties, etc., etc. And when we apply clustering, if the algorithm detects clusters in the data, it will basically take the dataset, and for each object, it will assign a class without us knowing whether there are classes in this dataset. In dimensionality reduction, we can take a very complicated dataset with a lot of measured features, and what the algorithm will do, it will output the same dataset, but now it will be represented using a low dimensional space, like 2D or 3D, so we can visualize the dataset. And we can also do outlier detection. So input dataset, and then in the output, the algorithm will mark anomalous objects, outliers. And why is it important? Why should we as scientists apply unsupervised learning to our algorithms? There are various examples. So first of all, in terms of clustering, imagine that I have a dataset with many different features, and I have a clustering algorithm that told me that the dataset consists of 3 classes. And imagine that this dataset is of planets. If I have 3 different classes of planets, perhaps it might suggest that these different classes have different formation mechanisms, different planet formation mechanisms. So it can teach me something about the physics of the systems that I'm working with. And obviously here I'm showing you a 2-dimensional dataset, but when we have a 2-dimensional dataset, it is very easy to visualize the dataset and to find clusters. But what should we do when we have a dataset with hundreds of features? For dimensionality reduction, I think this is my favorite example. On the one hand, we have optical stellar spectra. And if we look at these optical stellar spectra, without knowing too much about them, they appear extremely complex to us. Okay, there is this continuum emission that changes from one source to the next. There are various absorption lines that come and go. It appears as though we will need a lot of parameters and a very complicated model in order to explain this rich behavior. But on the other hand, we know that if we plot the same stars on the color magnitude diagram, where here basically every point is a star that has a stellar spectrum, what we find out is that all of these stars, most of them, occupy a very thin region in this diagram, which we call the main sequence. What does it tell us? It tells us that this entire complexity that we see here on the left can be expressed in terms of these properties, or in terms of the physical properties, the temperature and the luminosity of the star. So dimensionality reduction algorithms is basically taking something like this and representing it in a low dimensional space. And if in the start of the 1900s, the scientists that had these spectra had the dimensionality reduction algorithms we have today, they would have obtained the HR diagram much faster, and they could learn about physics of stars faster. Outlier detection, I think it is self-explanatory. Outliers are new anomalous phenomena in our dataset, and they can teach us something new about our datasets. And since we can no longer, since the datasets are so large and we can no longer inspect the datasets by hand, we want automatic algorithms to do that for us. Rodrigo, can you please tell me how long, how much time I have left?
We are reaching for the 40 minutes now. We can go 10 minutes, no problems.
Thank you very much. Okay, great. Okay, so this field of unsupervised learning is also extremely large, and unfortunately, I will not have time to show you different algorithms and different applications, because I want to show you a few examples of the things I've been involved in. So if you're interested in learning more about unsupervised learning algorithms and their applications, you can go to these two papers and read about it. So in the 10 minutes I have left, I want to ask two questions. Given this data revolution, and given that we can no longer inspect the data by eye, how can we discover new types of objects? How can we discover new phenomena in our datasets? The second question I want to ask, given the complexity of our dataset, how can we discover new trends and correlations in the dataset? So the first thing I'm going to discuss is the search for the unknown unknowns. What are outliers essentially? So when I think about my dataset, outliers can be bad objects. These can be various problems in the instrument, pipeline errors, etc. We can also have misclassified objects. So for example, a star in a catalog of galaxies. Outliers are also tails of well-characterized distributions. So the most massive black hole, the most luminous supernova, it will be an outlier because it sits on the tail of a distribution. And the most interesting types of outliers are what I call the unknown unknowns. These are completely new types of objects we do not know exist in our datasets, and we want to find them, and we do not know how to look for them. And the important thing to note is that in astronomy, outliers are not always rare phenomena. What do I mean by that? In astronomy, for example, these can also be processes that happen on much shorter timescales. So if I have a galaxy and the dynamical timescale of a galaxy is of order of hundreds of million years, imagine that every galaxy in the universe, something happens to it, a process that takes place over a period of 1,000 years or 1,000,000 years. What is my probability of detecting a galaxy during this phase, during this process in a large data set like the Sloan Digital Sky Survey? So the probability is very low. And this is just because the time scales are very different. So even if this process is extremely important and happens in every galaxy in the universe, it will appear as an outlier in my dataset. So in this paper here, we used an unsupervised random forest algorithm to assign distances between 2 million galaxy spectra from the SDSS. And basically, this is an unsupervised learning algorithm. It knows nothing about galaxies or spectra, but it learns the structure of the data through the mutual correlations between the features. And we defined the outlying galaxies as galaxies that have large distance from the rest of the galaxies. And we inspected the 400 weirdest galaxies, and this revealed a very diverse group of outliers. You can see here our classification for the type of outliers that we found. So for those of you who like galaxy spectra, I'm showing you here a few examples of outliers. This is a supernova exploding in the galaxy while the SDSS took a spectrum. This is an AMCVN star. This is, for example, a galaxy in which the sulfur-2 line is insanely large compared to what we usually expect. Here you can see an extremely reddened galaxy. Here you can see two sets of all the emission lines we see in galaxies. And here you can see double peaked emission lines. So we found a lot of very interesting objects there. And in fact, we found there one system, a post-starburst E+A galaxy with AGN N outflows. And this was a subtype, a subclass of objects we did not know existed before. And this became my PhD project. This is basically, we started a large follow-up campaign following these objects up with ALMA and NOEMA and different optical IFUs and X-ray in order to examine and study these objects. The second thing I want to ask is how can we find correlations and patterns in our dataset? And this is basically similar to me asking the question of what is there in my dataset? And here you can see an example of a dataset. You can see here one-dimensional objects, okay, some intensity varying as a function of pixel. And here, this is the same data set where here, every row represents one object and the color coding is according to the relative intensity in each pixel. And when we look at this data set, we don't know what is going on there, okay? We do not know what type of objects there is there, what type of physics we have there. But if we reorder the dataset, the objects in the dataset in some meaningful way, perhaps we can understand what is the physics there. So if we do that, we get this image here. What I did here, I took Einstein's image and I shuffled the rows in the image, and this was my dataset. Every row is an object. So in Baron and Menard 2020, we presented an algorithm that detects one-dimensional sequences in the dataset. If such sequence exists, it reorders the objects in the dataset according to this sequence and outputs it. So in this particular case, the algorithm have found a very significant sequence, which is Einstein's face, and it reordered the lines according to this sequence. These are two examples from astronomy where we basically recover the stellar sequence and where we recover the redshift sequence, where we give spectra of quasars in observer frame, and the ordering, the result of the sequencer is basically all the objects ordered according to the redshift, where the algorithm does not know what the redshift is. So we made one discovery, two discoveries with this tool. One of them is related to astronomy. We applied this tool to type 1 AGN spectra and found a new correlation between the narrow and broad emission lines in these sources. This correlation allowed us to present a new method to estimate the supermassive black hole mass in obscure type 2 AGN. So it taught us something new about AGN and about how we can measure their mass. Some final remarks. The algorithms I've presented, my own work, can be found, the algorithms and all the code can be found here. It's all public. In terms of the things I've presented, so supervised learning algorithms have allowed us to automate a large variety of tasks, basically taking the human out of the loop. It provided us speed and computational ease. In recent years, specifically deep learning have actually allowed us to do things we couldn't do before, like detecting these strong gravitational lenses and detecting stellar feedback features. The final thing I want to note is that unsupervised learning algorithms are also very interesting, and I really encourage you to try and use them and apply them to your datasets, because they can be used to extract new knowledge from existing datasets, knowledge we did not have because we do not provide a target variable, and they can therefore be used to facilitate new discoveries. That's it. Thank you very much.
Thank you very much, Dalya, for this remarkable, interesting presentation. We now have some time for questions from the audience. I'd like to remind, if you joined us on YouTube, you can put your comments in you can ask your questions via the comment sections. And if you joined us on Zoom, you can ask your question yourself. I'm going to start with a YouTube question. You were talking just about applying machine learning to spectra. So Marcelo Cup have a question, and he says, I'm studying machine learning and I would like to apply it to analyze the spectrum of light. Do you have any tools on how I can do that?
Of what? I'm sorry. What?
Apply it to analyze the spectrum of light.
The spectrum of what?
Of light.
Of light.
Yeah.
Spectrum, spectra, basically, spectra
Yes.
of objects.
I suppose yes.
Okay. Yes. So there are various tools to do that. Let me. So it is easier to do these kinds of things with more complicated models. Wait. Oops, sorry. So with more complicated models, it is easier to do these kinds of things. Models such as convolutional neural networks are very suitable for things like this. So this is a more complicated example, but here we actually have both a spectrum and two spatial dimensions. But I would note that not only deep learning can be used to classify spectra. Random forest, this is from my own experience, random forest is also capable of classifying, applying basically machine learning to spectral data. So I would suggest to start with simpler algorithms such as random forest, and only if this doesn't work, to go to more complicated models like convolutional neural networks. But in this, where is it? In this review here, you can find a lot of examples here too. You can find a lot of examples of how people applied machine learning algorithms to spectroscopic information. I hope this answers your question.
Thank you. More questions from the audience? Rogério Rosenfeld, please go on.
Yeah, I have a question, Dalya. Thanks for the talk. It's about the your algorithm for finding sequences and unscrambling Einstein space. I didn't quite understand what was actually done. I mean, what the algorithm has found. How did it figure out the what? Yeah, I don't understand what the algorithm has found in order to unscramble and get to Einstein space. I'm sorry.
Yes, no. That's a very good question, because I didn't go into how this algorithm works, because it can be a topic of a seminar by itself. But basically, what is going on there? We're trying to find a very elongated manifold in some high dimensional space. So my objects, I can think of them as entities living in a very high dimensional space, and from some views, they will appear as very elongated, so a sequence in a sense. How do we do that? So we use graph theory to do that. First of all, we take the objects and we need to assign distances between them in some way. You can do that using different ways. But imagine that I have these distances, then I can represent my entire data set as a fully connected graph, because every object is a node in this graph, and every node is connected to every other node in terms of the distance. And then I can calculate a graph property, a very interesting graph property that is called the minimum spanning tree. This is basically the backbone of the graph, the minimal structure that will still allow me to reach from every object to every object. And apparently, the geometry of this minimum spanning tree holds a lot of interesting information about the structure of the data. And if this minimum spanning tree is very elongated, it strongly suggests that there exists a one-dimensional sequence in the data. So what the algorithm does, it optimizes over different distances and different scales, trying to find this elongated structure. And if it found it, it reorders the objects according to this structure. So from here to here, the only thing that changed is the relative order of the objects. But once things are presented like this, it is much easier for us to understand what is going on there. So this is how the algorithm does that. And the code is online. We also have a web page where you can upload your data set, and the web page will reorder the data set, will apply the sequencer to it. So if you're interested, you can either go here and find it, or you can email me. I'll be happy to point you out to the different things that we provide.
Okay, so it's much more complicated. Thank you. And just, I read a paper that was fascinating that, I don't know exactly what neural network was used, but I think people input the orbits of the planets, and the algorithm found out that the system was heliocentric, our planets, that the system was heliocentric. That was impressive. From the Earth,
yes.
The orbit from the Earth, and then the algorithm found out that the question is whether you can find Newton's gravitational law from this data. That's something that will be very interesting. Thank you.
Thank you. Thank you, Rogério. Now, Roberto, please, the floor is yours.
Hello, Dr. Baron. Thank you for your very interesting presentation. I'm curious about the overfitting problem in the most complex models like deep nets. I would like to know which more critical for the overfitting problem, having redundant or non-informative features, or misleading in the construction of the net itself, and how can we keep it under control?
Excellent question, Roberto. Thank you very much. Okay, so when we talk about deep networks, these things can have so many free parameters that they can actually remember by heart the examples I give them. So imagine that my data set has 2 images, and each image is 10 by 10 pixels. Okay, so 100 pixels in total. And imagine that I'm training a network that has 10,000 neurons. So this network can basically remember by heart the entire image. So basically, if all the pixels are like this and this and this, this is a cat. If all the pixels are like this and this and this, this is a dog. So this is essentially why these networks overfit, because they have so many parameters that they can do that. In order to avoid that, we divide our data set, the data set in which we know the labels, into 3 data sets. I talked about the training data set. This is the data set on which the algorithm trains. Then we have a data set that is called the validation data set and the training data set, and the test data set, sorry. So the algorithm is trained only on the training set. It does not see the validation set or test set. The validation set is used to optimize various hyperparameters of the network. So how many layers should I use? What type of nonlinear functions I should apply, etc. But then I have my test set. These are objects for which I have the class, but the algorithm didn't see them. And once I'm starting to train the network step after step, this is an iterative process, I can see what is the accuracy of the prediction for the training set and for the test set. So when an overfitting starts, the accuracy for the training set improves and improves and improves, because the algorithm basically learns by heart the examples. But what happens in the test set, the objects that the algorithm did not see? There we see a decrease in the accuracy. In the number of objects the algorithm is properly classifying. Let me, I have, let's see if I can find it quickly, a diagram that shows it. And basically through this method, if I'll not find it in shortly, I will stop looking for it. There you go. Okay. So if I look at the error in terms of not accuracy, so error, this is the opposite from accuracy, the error rate that my algorithm has. For the training set, it will always decrease, even when the algorithm starts to learn by heart the examples. But for the objects that the algorithm did not see, at some point the error starts to be larger, because for these objects, it did not learn it by heart. And this is why it is very important to divide our data set where we have the labels into training, validation, and test sets.
Okay.
Thank you, Dr. Baron.
You're welcome.
Okay, thank you, Roberto. I think we can have a last question. Okay, well, I have a question as well. You showed that we have different, when we apply different types of machine learning, we have different different number of free parameters. That wasn't actually very clear to me. Why isn't it dependent on the model that I'm trying to fit? Or why do I only have 4 free parameters in the vector machine example, for instance, if I want to fit something complex?
Yes, no, this is a very good question. So there are 2 types of parameters that we have in our model. The first type of parameter is parameters we do not control. The model learns the parameters by itself. So we do not have any control over these parameters. So for example, in deep learning, in neural networks, these are the actual neurons and the weights of each neuron, okay? And these can be millions. The free parameters here, what I call free parameters, I should have called it hyperparameters. These are the parameters we can control, okay? So what type? This SVM is not a single algorithm. It's a family of algorithms. And there are different choices I can make within this algorithm. So I can use one type of boundary to divide objects or a different type of boundary. In the random forest, for example, I need to decide how many trees do I want in my forest. Do I want 10? Do I want 100? Do I want 1,000? And all of these things will have an effect on the output that I will get, on the accuracy, on how well I can do machine learning. And in deep learning and artificial neural networks in general, there are many of them, because I can decide how many layers I'll have, how many neurons per layer, what type of activation function. There are many, many, many things I can choose. And this is why these networks are extremely difficult to build. As a person who is not used to deep learning, it is very difficult to know in advance what is the correct architecture to use. And all of this architecture is basically what I call the free parameters. These are our choices, and these are things we control.
Okay, now it's clear. It was actually confusing different types of parameters. Well, thank you.
You're welcome. It was very nice.
Yeah, thanks. If we do not have more questions, we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. And for the next week's webinar, we will have Wagner Corradi. He is the director of the Laboratório Nacional de Astrofísica. So thank you everyone for attending, and a special thanks for Dalya. Thank you, Dalya.
Thanks, Rodrigo.
And everyone, have a great day, stay safe, and I hope to see you all next week. Thank you.
Bye.
Bye-bye. Thanks.